Hi all, we now see an interesting real valued function that is continuous at every single point on the real line, but not differentiable at any point. That is, there exists a function that is continuous on the real line, but differentiable at no points. The construction of the function is in 4 stages. We construct the function in the first 2 stages, and in the next 2 stages, we see that it satisfies our requirements. In stage 1, we define a function phi on the interval minus 1 to 1. Let phi of x be equal to mod of x for all x in the interval minus 1 to 1. It is our standard V-shaped absolute value function. It is a continuous function on the entire interval minus 1 to 1, but is not differentiable inside at the point 0. We extend the function phi to the whole of the real line by fixing phi of x plus 2 is equal to phi of x. This is known as the periodic extension of phi. There are very many interesting properties associated with this new function phi. Let us see them one by one. The foremost one is phi is a continuous function on the entire real line. The second one is phi is a non-negative function. 3. Phi is a bounded function with minimum 0 and maximum 1. It is 0 at all even integers and 1 at all odd integers. It is not differentiable at all integer points. It is periodic with period 2. Phi of x is equal to x for all x in the interval 0 to 1 and 2 minus x for all x in 1 to 2. We can generalize this. Phi of x is equal to 2n minus x if x is in the interval 2n minus 1 to 2n, and phi of x is equal to x minus 2n if x is in the interval 2n to 2n plus 1 for all integer n. In addition to these, phi of y minus phi of x is equal to y minus x if x is less than y and are both in either 2n minus 1 to 2n or 2n to 2n plus 1 for every integer n. That is, both x and y are lying in one single interval of length 1 between any two integer points. We use this function phi for constructing a sequence of continuous functions on the real line in the next stage. For each natural number n, define fn of x as 3 upon 4 power n into phi of 4 power n into x for all x in R. Fn is a sequence of positive real numbers that converges to 0 as n tends to infinity. Hence, the series Fn converges, say, to a function f, that is, f of x is equal to summation n varying from 0 to infinity Fn of x. As f is sum of continuous functions and the convergence is uniform, we can see that f is also continuous. It is continuous everywhere on R. We now analyze the differentiability of f. This is done in the next stages. For each positive integer m and for every real number x, we can find an integer k such that k is less than or equal to 4 power m into x less than or equal to k plus 1. For example, if x is an integer, 4 power m into x itself is the k or k plus 1. As 4 power m into x is a real number, it is not hard to find such a k. Having found such a k, we divide the above inequality by 4 power m. Hence, we now put alpha sub m as k by 4 power m and beta sub m as k plus 1 by 4 power m. We get two different sequences. Beta sub m minus alpha sub m is 1 upon 4 power m. As m approaches infinity, 1 upon 4 power m approaches 0. Moreover, we see that x is sandwiched between alpha sub m and beta sub m. As m approaches infinity, the sequence alpha sub m and the beta sub m approach to x from left and right respectively. It is not difficult to prove that for two such sequences, limit m tends to infinity, f of beta sub m minus f of alpha sub m upon beta sub m minus alpha sub m is f dash of x. This is purely theoretical. In this particular case of alpha sub m and beta sub m, let us evaluate whether this would exist or not. This is the final stage. F of beta sub m minus f of alpha sub m is equal to summation n varying from 0 to infinity 3 by 4 power n into phi of 4 power n into k plus 1 upon 4 power m minus phi of 4 power n into k upon 4 power m. Let us evaluate phi of 4 power n into k plus 1 upon 4 power m minus phi of 4 power n into k upon 4 power m. Case 1. When n is greater than m. Here phi of 4 power n into k plus 1 upon 4 power m minus phi of 4 power n into k upon 4 power m becomes phi of 4 power n minus m into k plus 1 minus phi of 4 power n minus m into k. That is phi of an even integer minus phi of another even integer. But when we see the properties of phi, we had seen that phi of an even integer is always 0. Therefore, both are 0 and hence all terms in the sum from m plus 1 vanish. Case 2. When n is less than m. Here phi of 4 power n into k plus 1 upon 4 power m minus phi of 4 power n into k upon 4 power m becomes phi of 4 power n minus m into k plus 1 minus phi of 4 power n minus m into k. But both these terms 4 power n minus m into k plus 1 and 4 power n minus m into k lie between two consecutive integers. Hence, as we observed earlier, it becomes just 4 power n minus m into k plus 1 minus 4 power n minus m into k, that is 4 power n minus m. You go to case 3, when n is equal to m. Here, phi of 4 power n into k plus 1 upon 4 power m minus phi of 4 power n into k upon 4 power m becomes just phi of k plus 1 minus phi of k. It is 1 and just we write it as 4 power n minus m as n minus m is 0. Hence, f of beta sub m minus f of alpha sub m reduces to just summation n varying from 0 to m 3 by 4 power n into 4 power n minus m. Cancelling 4 power n and pulling out 4 power minus m from the sum, we get f of beta sub m minus f of alpha sub m is 4 power minus m into summation n varying from 0 to m 3 power n. Hence, f of beta sub m minus f of alpha sub m upon beta sub m minus alpha sub m is summation n varying from 0 to m 3 power n. That is, it is equal to 3 power m plus 1 minus 1 upon 3 minus 1, that is 2. As the limit m tends to infinity, 3 power m plus 1 minus 1 upon 2 diverges. Hence, the derivative of f does not exist at x. As x is arbitrary, we conclude that f is nowhere differentiable. Thank you.